Have you ever watched a bouncing ball and wondered, does it ever actually stop, or is it trapped in an infinite loop? This chart shows the exact motion. With a perfectly elastic ball, every bounce is shorter and faster than the one before it. Because the time between impacts shrinks towards zero, the timeline clusters into a solid block, fitting infinite bounces into a finite time. Our physical reality routinely hides these infinite processes. We perform impossible, infinite tasks every time we drop an object, or even take a step forward. The Greek philosopher Zeno noticed this over 2,000 years ago. He pointed out that to walk anywhere, you first have to reach the halfway point of your journey. From there, you have to cross half of the remaining distance, then half of that new distance, over and over again. So to simply walk across a room, you actually have to complete an infinite number of smaller journeys. Modern philosophers push this idea even further. Imagine an endless line of white billiard balls, each one smaller and faster than the one before it. The first ball strikes at exactly half a second. The next hits a quarter of a second later, the third an eighth of a second later, and so on. Because of this shrinking schedule, the entire infinite chain of collisions finishes in exactly 1 second. These thought experiments force a strange question. Is the end of an action an actual physical barrier we cross, or just a mathematical trick we use to make sense of the world? In 1954, James F. Thomson designed a thought experiment, a lamp with a toggle button. You start a timer. At 1 minute, turn it on. Half a minute later, off. A quarter minute later, on. This shrinking series of intervals sums to exactly 2 minutes. As the clock nears the 2-minute mark, the switching accelerates into a frantic blur. The clicks merge into a hum, the bulb flashing infinitely fast. The clock hits 2 minutes. But we have absolutely no method for deciding what state the lamp is in when that final second ticks over. At exactly 2 minutes, after an infinite number of toggles, is the lamp on or off? It can't be on. The rules of the experiment guarantee that every time the lamp was turned on, a subsequent action immediately turned it off. But it can't be off either, because every time you turned it off, another click was scheduled to turn it right back on. This is a pure logical contradiction. We've set up strict physical conditions, followed them perfectly, and arrived at a result impossible to determine. We assume a sequence of strict deterministic actions will eventually produce one clear, inevitable outcome. Thomson's lamp proves that assumption wrong. What Thomson designed is called a supertask, a countably infinite sequence of operations carried out within a finite interval of time. In mathematics, an infinite series can easily converge on a finite limit. But physical actions are different. A sequence of real-world events usually requires a final step to be considered complete. The philosopher Paul Benacerraf offered a brilliant counterargument. He pointed out that knowing the state of the lamp at every point before 2 minutes tells us nothing about its state at 2 minutes. The final state is completely independent of the sequence that came before it. We are left staring into a gap in logic. The instructions for the supertask describe the journey perfectly, but they leave out the destination. Supertasks reveal a missing final frame in our understanding of reality. They show us exactly where our intuition about infinity crashes into the rigid flow of time. In reality, friction and physics stop the bouncing ball, but in the realm of pure logic, processes can run forever without ever reaching a final step. This gap in reasoning marks the boundary where our best models of the universe, from classical mechanics to relativity, reach their absolute limits. A moment of wonder. We often think of infinity as an endless expanse,